In this lesson, we're going to talk about applying transformations to both individual points and to parent functions. When applying the principles of transformations to help us graph complicated functions, it's vital for us to know what the parent function is and to know the values of a, k, d, and c. It's important to remember that the input of a function using our transformation principles is k bracket x minus d, and also to remember our mapping formula, which is shown here. There are other ways of determining points on a transformed function. There's people use columns and charts, and they're all good methods. For our purposes, I use the mapping formula. Imagine the point 5, 6 is a point on the curve y equals f of x. Well, if we want to determine a point on the curve y equals 5 plus 2/3 f of 1/4 x minus 3, we're going to have to do a few steps. First of all, we're going to rearrange the expression to match the form y equals af of kx minus d. So what we're going to do, first things first, is take that 5 and move it over, and that'll give us 2/3 f of 1/4 x minus 3 plus 5. Then we're going to factor the input, which is also called the argument. Factor out that 1/4 and we get x minus 12. Now we know that a is 2/3, k is 1/4, d is 12, and c is 5. Now xy will map onto x over k plus d and ay plus c. So since the point I'm being asked to transform is 5, 6, that means x is 5 and y is 6. And I know the values of a, k, d, and c, so I can just plug them in right here. And then I do a little evaluation. To the left of the comma, I have 5 over 1/4 plus 12. To the right of the comma, I have 2/3 times 6 plus 5. Ultimately, what I get is the point 32, 9. So we say that the point 32, 9 is on the curve y equals 5 plus 2/3 f of 1/4 x minus 3. The point 32, 9 is called the image of the point 5, 6. Now let's suppose that the point negative 4, 10 is a point on the curve y equals 7 minus 3f of 6 minus 1/2 x. We want to determine a point on the curve y equals f of x. Well, this is a reverse of the first question. It's a backwards question. Because in the last question, what happened is we were given a point on y equals f of x. Pardon me, y equals f of x, and we were asked for a point on the transformed curve. Well, in this question, we're given a point on the transformed curve, and we're asked to go backwards and determine a point on the curve y equals f of x. So, in essence, what that means is the point that we are given, which is negative 4, 10, is x over k plus d and ay plus c. They want us to tell them what x and y are. Okay? So the point negative 4, 10 is the point x over k plus d and ay plus c, and we're trying to work backwards to the point xy. So we can start by saying negative 4 is x over k plus d, and 10 is ay plus c. And we'll refer to those as equation 1 and equation 2. Now let's determine the values of a, k, d, and c. What we're going to do is we're going to take this 7 that's in front, we're going to move it to the end, which means we've got negative 3 f of 6 minus 1/2 x plus 7. Then we're going to rearrange these terms to put the x term in front. And then we're going to factor out negative 1/2 from that input and have negative 1/2 bracket x minus 12 bracket. What that means is that a equals negative 3, k equals negative 1/2, d equals 12, and c equals 7. Recall equation 1. Equation 1 said that negative 4 equaled x over k plus d. Well, k is negative 1/2, d is 12. So that means negative 4 equals x over negative 1/2 plus 12. Subtract 12 from both sides, multiply both sides by negative 1/2, and we get x equals 8. Recall from equation 2 that 10 was equal to ay plus c. Well, we know a is negative 3 and c is 7, so 10 was equal to negative 3y plus 7. We can subtract 7 from both sides, get 3 equals negative 3y, divide both sides by negative 3, and we get y equaling negative 1. So x is equal to 8 and y is equal to negative 1. We're trying to figure out what the point xy is. So obviously the point xy is the point 8, negative 1. So that point is on the curve y equals f of x. Let's talk about the square root function now. When the parent function is f of x equals the square root of x, then the input goes underneath the radical sign. Then we multiply the result by a, we can quote put a in front, and add c to the result, we can add c at the end. So ultimately what we're trying to do is rearrange algebraically the equation we're given to look like this. And we want to remember that three key points are 0, 0, 1, 1, and 4, 2. So suppose you want to graph the curve y equals 4 minus 5 times the square root of 1/2 x plus 3. Well, right away, we know from the last slide that we're trying to get our function to look like this. So what we can do is move that 4 to the far right. Then our next move is going to be to factor the 1/2 inside of the radical sign, inside the input. When we do all that, we end up being able to say that a is negative 5, k is a half, d is negative 6, and c is 4. Since it says x plus 6, we remember that d is negative 6 because we're always changing the sign in front of d. So a is negative 5, k is a half, d is negative 6, c is 4. We recall that three key points on our original function are 0, 0, 1, 1, and 4, 2. So we can take those 3 points and put them through the mapping formula. So knowing that a is negative 5, k is a half, d is negative 6, and c is 4, we first let x and y be 0 and 0. Putting them through the mapping formula, we end up with negative 6 and 4. Then we let x and y be 1 and 1, but we still let a, k, d, and c be the values that we've already determined. We then go through the mapping formula like in the second row, and we end up with the point negative 4, negative 1. And finally, we let x and y be 4 and 2, because 4, 2 is a point on the parent function. And we let a, k, d, and c be the values highlighted above in the in the red rectangle. And so when we put 4 and 2 through the mapping formula, we get the point 2, negative 6. So we plot those 3 points, and this is what they look like. It's important to remember that the point up at the top there is the transformed point 0, 0. In other words, it's the image of the point 0, 0. That means that's the point where the curve is going to begin. In other words, the point without the arrow. Because if you recall, the parent function looks like this. 0, 0 is down here, and it does not have the arrow. So I draw a curve going through, starting at that point and going through the others and having an arrow. And I'm able to say what the domain and the range are by using the principles that we already know. Now, this question also wanted us to state the transformations. When a is negative 5, we have had a reflection in the x-axis and a vertical stretch by a factor of 5. When k is equal to a half, we've had a horizontal stretch by a factor of 2. When d is negative 6, we've had a translation left 6 units. And when c is 4, we've had a translation up 4 units. What if we want to graph an absolute value function? Well, when the parent function is f of x equals absolute value of x, then the input goes inside the straight absolute value brackets. It says here the radical sign, but that shouldn't be there. The input goes inside the straight absolute value brackets. Then we multiply the result by a, in other words, put a in front, and add c to the result. So add c at the end. So we want to rearrange the function to look like what we've got written at the bottom. Whoops, and just trying to get my pen back. There we go. We want to rearrange algebraically so that it looks like that. And we're going to remember that 3 key points are negative 1, 1, 0, 0, and 1, 1. So given that function right there, we're able to say pretty quickly without much manipulation that a is 3, k is 1, d is 4, and c is 2. And we know the points on the parent are negative 1, 1, 0, 0, and 1, 1. So we're going to let x and y equal -1 and 1. And we already know what AKD, whoops, I didn't mean to cross that out. We already know what AKD and C are, so we'll apply the mapping formula. Then we'll let x and y be 0 and 0, let AKD and C have the same values, and apply the mapping formula. Then we'll let x and y be 1 and 1. We already know what AKD and C are, and we'll apply the mapping formula. Now, when we do that, we get the points 3, 5, 4, 2, and 5, 5. It's our job now to plot a function, that goes through 3, 5, 4, 2, and 5, 5, and mimics the behavior of the parent. And that's what it would look like. The domain would be the set of all x element of the reals, and the range would be the set of all y element of the reals such that y is greater than or equal to 2. To state the transformations, if a equals 3, there's a vertical stretch by a factor of 3. If k equals 1, there's no transformation. If d equals 4, there's a translation right 4 units. And if c equals 2, there's a translation up 2 units. Now, how about the cubic function? When the parent function is f of x equals x cubed, then the input is the quantity being cubed. We can put that quantity in brackets and raise it to the exponent of 3. Then we multiply the result by a. We can quote, put a in front, unquote, and add c to the result. We can add c at the end. So therefore, we should try to arrange the function to look like this at the bottom. So you might notice now a pattern. We're always trying to get the function algebraically manipulated to look like such a way that we can determine quickly what a, k, d, and c are. And if you're really paying attention, you'll notice there's some similarities in here. Very, very, very much so. Now remember that the three key points are -1, -1, 0, 0, and 1, 1. Those points are specific to the parent function x cubed. So now we graph this curve, -2 plus 1/2, -4 minus x quantity cubed. Well, what we're going to do is algebraically manipulate it. We'll put that -2 on the end, and that's going to be our c value. And we'll put that -2 on the end. And then we'll have that 1/2 in front. We're going to want to rearrange the argument or the input of -4 minus x, and then factor that -1 out in front. And when we do all that manipulation, we end up with a equaling 1/2, k equaling -1, d equaling -4, and c equaling -2. We know the three key points, we know the mapping formula, and we get to work. -1, 1 maps onto -1, 1 maps onto -3, -2.5. 0, 0 maps onto -4, -2, and 1, 1 maps onto -5, -1.5. We plot those 3 points. And at first glance, those 3 points just look like that. Now, sometimes students put the wrong thing down. They might make a curve that looks like that, but that's wrong because that doesn't mimic the behavior of the parent function. They'll put a curve that looks like that, but that's wrong as well. Sometimes they'll make something weird like that with some pretty weird stuff going on in the middle there. That's incorrect. This is what it looks like. Okay? Now, some people find it difficult to remember that. So what some people do is they will also transform the point -2, -8, and 2, 8. Now, why would they do that? Why would they do those 2 points? Well, the point -2, -8 is on y equals x cubed because -8 equals -2 quantity cubed. Literally, y equals x cubed. And similarly, 2, 8 is on y equals x cubed because 8 is equal to 2 cubed. In other words, y equals x cubed. So we're able to use as many points as we want, and these are a couple more options for us. So I've seen students use not just 3 points, but actually transform 5 points. When they do that, they get the point -2, -6, and -6, 2. Those points are there, which allows them to draw a really good curve. So, and the domain would be the set of all x element of the reals, and the range would be the set of all y element of the reals. Now, is it necessary to do that? No, not if you don't need to. But if you need to, do it. It's an option for you. Now we want to verbally state the transformations. A is a half. That means there's a vertical compression by a factor of a half. K is -1. That means there's a reflection in the y-axis. D is -4, which means there's a translation left 4 units. And C is -2, which means there's a translation down 2 units. And now let's talk about the reciprocal function. When the parent function is f of x equals 1 over x, then the input is the quantity in the denominator. Then we multiply the result by a, which is the same as making the numerator a, and then we add c to the result, adding it at the end. So what we want to do is arrange the function to look like this. And two key points are going to be -1, -1, and 1, 1. But we won't just have two key points, we're also going to have two asymptotes here. And that's what the small font is telling you. The vertical asymptote of the parent function is x equals 0. When we put an x value of 0 through the x portion of the mapping formula, i.e. x maps onto x over k plus d, we ultimately end up with 0 mapping onto d. So the new vertical asymptote will be x equals d. It'll always be that way when you're dealing with this specific parent function. And the horizontal asymptote of the parent function is y equals 0. When we put a y value of 0 through the y portion of the mapping formula, ultimately we get 0 mapping onto c, which means that the horizontal asymptote of the transformed function will be y equals c. So that we've got actually 4 nice pieces of information, 2 points and 2 asymptotes. So what if I ask you to graph the curve y equals -1 over 2x minus 5 and then quantity subtracting 5? Well, what we do is we determine, first of all, that a is -1, k is 2, d is 3, and c is -5. Then we put our two key points of -1, -1, and 1, 1 through the mapping formula. When we do that, we get the points 2.5, -4, and 3.5, -6. All right, that's good to know. But we should also know that we're going to have a horizontal asymptote at y equals c and a vertical asymptote at x equals d. So we're going to have a horizontal asymptote at y equals -5 and a vertical asymptote at x equals 3. Two asymptotes, two key points. We plot them. Now what we want to do next is we want to treat asymptotes like asymptotes, and our curve ultimately ends up looking like that. And we're able to say that our domain is the set of all x element of the reals such that x doesn't equal 3, and our range is the set of all y element of the reals such that y doesn't equal -5. Our transformations are a equals -1, meaning there's a reflection in the x-axis, k equals 2, meaning there's a horizontal compression by a factor of a half, d equals 3, meaning there's a translation right 3 units, and c equals -5, meaning there's a translation down 5 units. We're not going to deal with the exponential function right now, and we are not going to deal with sine x and cos x right now, but we'll jump towards the end. And let's say we've got an odd looking function like the one here, what I would call an irregular function. We want to graph the curve y equals -1/2 f of -1/3 x plus 1 minus 2. Well, in order to do that, we should know points on the parent function. And the points that we know are the points -3, -4, 0, 6, and 1, -2. If we can transform those 3 points, we're going to have a pretty good potential for determining what the graph of the transformed function looks like. So we determine that a is equal to -1/2, k is equal to -1/3, d is equal to -1, and c is equal to -2. And we take turns with each of those 3 points, plotting them, putting them through the transformation mapping formula. So we start with -3, 4, and we ultimately find out that -3, 4 maps onto 8, 0. Sorry, -3, -4 maps onto 8, 0. Then we have 0, 6, which is on the parent, and ultimately that maps on to -1, -5. And we have 1, -2, that's also on the parent, and ultimately 1, -2 maps onto -4, -1. So we're going to plot those 3 points in red. Then we're going to draw the best curve that we can. Since we draw a straight line from the from -3, -4 to 0, 6, we're going to draw a straight line from the image of -3, -4 to the image of 0, 6. Then we're going to connect that with a straight line. Since the original function goes from 0, 6 to 1, -2, we'll go from the image of 0, 6 to the image of 1, -2. And since the original function moves to the right horizontally after that, and since our curve has a reflection in the y-axis, we will move to the left horizontally. So ultimately, that's what our function is going to look like. Okay? Now, this is the explanation of why our original curve goes to the right horizontally at the end. Ours is going to go to the left horizontally. The description of why that is here, essentially because we have a reflection in the y-axis, and we know that because k is negative. And so our curve ends up looking like that. The part that's hard for some students is knowing that the arrow now points to the left. So if the explanation I gave you earlier doesn't do it for you, then another method is to simply plug another point that the arrow goes through. And you might say, well, what other points does the original function go through? And I would say the original function goes through 2, -2. It also goes through 3, -2. It also goes through 4, -2. I can take any one of those points, put it through the mapping formula, and what that'll do is it'll transform me to a point out here, which will then allow me to properly graph the curve. So what we'll do is we'll try the point 2, -2. Since 2, -2 is on the original parent, we'll put it through the mapping formula, and it becomes -7, -1. So the image of 2, -2 is -7, -1, which is out here. And so we know that our arrow is pointing in the right direction. Okay. When in doubt, put more points through the mapping formula. However, my hope is that you understand patterns enough that you don't have to put too many through, and you can save yourself some time. And that's the end of this lesson, and I hope it was illuminating.